Hello BC Calculus students, this is Mr. Johnson and this is the second video for section 8.1. We're going to tackle a couple of these examples together. First I wanted to add one thing to theorem 4 from the previous video because remember this theorem is often used for situations where you have an alternator in a sequence, and so I wanted to give you just a couple common alternators. You will see often -1 to the power of n. You also will see -1 to the power of n plus 1. And those are common alternators which will cause a plus minus plus minus plus minus. You also might see a little bit of trigonometry in there, and I will show you examples of that as well. The other thing I wanted to mention was that you have odd alternators. So if you see an n plus 1, you see a 2n plus 1, an n minus 1, a 2n minus 1, a bunch of stuff like that. That is going to cause an odd number to continue to come out of the sequence. You also may see for even something like 2n as an even alternate or an even generator. Okay, so you have the alternators, you have the odd generators, you have the even generators. There's obviously more, but those are some of the ones that I wanted to highlight, especially the alternators connected to theorem 4. Okay, let's try example 1. So example 1, really the question here is, does the particular sequence converge or diverge? And so we're going to take the limit as n goes to infinity of n over n plus 1, and we get 1 here. We could use L'Hopital's to do this. I'll explain that in the next problem. But in this case, we're looking at the 1 in the denominator is insignificant as n goes to infinity. So you have n divided by n, which is just 1. So what we would say is that a sub n converges to 1. And in this case, we're letting a sub n equal n over n plus 1. Okay, in example 2, we'll do the same thing. Now in this case, we end up getting an infinite value in the numerator and an infinite value in the denominator. So in other words, if you analyze the limit as n goes to infinity of the natural log of n, you get infinity. And if you look at the limit as n goes to infinity of n, you get infinity. And so by L'Hopital's rule, we can actually take a look at this. And the reason we can do this, and it says this at the bottom of the page here, is because of theorem 2 of the previous page, where we're able to compare sequences and functions as long as the function is continuous. We can look at this with the context of L'Hopital's rule, which is really a function rule, but because we can compare these sequences with functions, then we can do this with this particular sequence. So we have 1 over n divided by 1, and as n goes to infinity, we get 0. So a sub n, which is the natural log of n over n, is convergent to 0. Okay, let's go to the next page and try example 3. All right, example 3 is a sub n convergent or divergent. So one of the things I would do with a problem like this is I would start to list terms. So if n was 1, and it doesn't really matter what we start with n. N is not negative, is never negative, but you could start at 0, you could start at 1, you could start at 7. It doesn't really matter. We're trying to look out at the end what happens. So it's sort of common just to start at 0 or 1. Let's say we start at 1, so we get -1, and then if n is 2, we get +1. If n is 3, we get -1. If n is 4, we get +1. And you get the idea. It's really clear by just simply listing terms that this particular sequence is going to be divergent. Now, because it has an alternator, let's say that you wanted to analyze the limit as n goes to infinity of the absolute value of -1 to the n. That would be the same as the limit as n goes to infinity of 1, because no matter what, if it's the absolute value, it's either going to be -1 or 1 each time. And if we take the absolute value, we simply just get 1. That limit is 1, which is not equal to 0. So utilizing theorem 4 on the previous page, we can't really apply it, because remember that theorem says that if the absolute value of the sequence is 0, then the original has a limit of 0. And so in this case, we can't apply that theorem, but just by by listing terms just by observation, we can tell that this particular sequence is definitely divergent. Okay, let's try the next one. So here, if we were to list terms out, let's see, I'll do that right here. So let's say that n was, let's do 1. We can't start at 0 because we can't divide by 0. So if n is 1, we get -1. If n is 2, we get a +1 over 2, so we get 1/2. If n is 3, we get a -1 over 3. If n is 4, we get a +1/4, and then so on. This one's a little bit harder to see what's going on. I mean, obviously it's alternating, it is decreasing, it's getting smaller, so it appears as though it may be approaching 0. One of the ways that we can definitively show this is that we can take the absolute value of this particular sequence. Remember, when we do that, that alternator becomes obsolete. So we have the limit as n goes to infinity of just 1 over n, and that's really easy to see that that limit is 0. And because that limit is 0 from that theorem on the previous page, theorem 4, we could say that since that limit is 0, then a sub n is, and a sub n, I'm making -1 to the n over n, is convergent to 0. So it converges to 0. Okay, this is not one of our examples, but we're going to do a little proof here utilizing the squeeze theorem. We're going to prove that a sub n is equal to n factorial over n to the power of n. The first 4 examples have been relatively easy, and I don't want to overwhelm you with this one, but this is a bit more complex. This is sort of at a different level. Now, one of the side notes that we need to talk about is factorial. So you've seen factorial. If not, you haven't paid attention to previous math classes before. Factorial is a notation. Let me back up. Let me do let's do 4 factorial. So factorial is a notation that takes on the pattern of the value multiplied by a number, the number 1 less than it, times the number 1 less than it, times the number 1 less than it, all the way to 1. So 4 factorial is 4 times 3 times 2 times 1. If you had n factorial, you have n times n minus 1 times n minus 2 times n minus 3, and so on. That continues until you get down to 3 times 2 times 1. Now, obviously, if n is 4, then it's not going to look as large as what I just represented. I'm sort of representing n factorial as if n was a much larger value, which obviously we're going to be looking at here because we're going to be looking at the values of n increasing indefinitely. So that's the definition of factorial. Sort of on a side note, it doesn't really apply to us here, but by definition, 0 factorial is equal to 1. And that will come up throughout our study. Okay, so let's go back to this problem. So we're going to prove that this particular sequence converges to 0, which it's kind of a bizarre sequence. Both the numerator and denominator are incredibly large values. And so what I'm going to do with this one is I'm going to use the squeeze theorem, but I'm going to start to set up terms prior to doing that. So a sub 1 would be when n is equal to 1. 1 factorial is 1. 1 to the power of 1 is 1. So I get 1 out of that. A sub 2 is equal to, in the numerator, 2 times 1, which is 2 factorial, divided by 2 to the power of 2, which is the same thing as 2 times 2. A sub 3 is equal to 3 times 2 times 1 in the numerator, and 3 to the power of 3 is 3 times 3 times 3. A sub 4 is equal to 4 times 3 times 2 times 1, and we get 4 to the power of 4, which is just 4 multiplied by itself 4 times, and I'll stop there. I won't keep boring you. We're going to do one more general term. So this is going to be a sub n, and that gives you n factorial, which is n times n minus 1 times n minus 2 times n minus 3, and so on, until we get down to 3 times 2 times 1. In the denominator, we have n to the power of n. So that's going to be n times n. I'm going to try to write out the same number here. I'll space them out so they're sort of lined up. Times n, and so on, times n, times n, times n. Now there's a pattern here that's forming. A sub 1 is not going to really help us very much. So I'm not going to worry about that too much right now. A sub 2, if you notice, the 2's cancel. A sub 3, the 3's cancel. A sub 4, the 4's cancel. A sub n, the n's cancel. Now aside from A sub 2, there's some sort of extra stuff that is in each of these. So for example, there's some extra stuff here, and there's some extra stuff here, and there's some extra stuff here. Now, no matter what, that extra stuff is less than 1. So that extra stuff is only going to make the value overall smaller because it's less than 1. The end of each of these, so for example, if we just focus our attention on this portion right here, we have 1/2, which is a sub 2. Now I'm going to write this as less than or equal to 1/2, just for the sake of illustration. For a sub 3, we of course have 1/3 right there, but keep in mind that the 2/3 right next to it would cause the 1/3 to actually be smaller. So what we could say is that a sub 3 is less than or equal to 1/3. A sub 4, we have the 1/4. And so we could say that a sub 4 is less than or equal to 1/4. Again, you have this 2 times 3 divided by 4 times 4. So really, overall, this is less than 1/4. But I'm just going to say it's less than or equal to 1/4. And then, of course, you have the very last one, which is 1 over n. And you might be starting to see sort of what we're trying to do here. But that's going to be less than or equal to 1 over n. So what we've done is we've shown that not only individual terms at the very beginning of this particular sequence follow a pattern, but the nth term, the ending term of this particular sequence also follows the same pattern. Now, because n is, because of our terms, n is going to be causing our terms to be greater than 0, what we could say is that our particular sequence, a sub n, is always going to be greater than or equal to 0, but it's going to be less than or equal to 1 over n, which we've shown here at the general term. We've shown that this entire term is less than or equal to 1 over n. So we can make a statement where we have squeezed the a sub n term in between 0 and in between 1 over n. I'm just going to write that as 0 is less than or equal to n factorial over n to the power of n is less than or equal to 1 over n. Now, if we were to take the limit as n goes to infinity of 0, that's equal to the limit as n goes to infinity over 1 over n, which is equal to 0. Maybe a better way to say that, let me back up. So this limit is equal to 0, as well as the limit as n goes to infinity of 1 over n. Probably a better way to say that. So both the ends of this compound inequality I've set up have a limit of 0. And so what we could say is that therefore by the squeeze theorem, the limit as n goes to infinity of n factorial over n to the power of n must also be 0. And we could conclude by saying therefore a sub n, which is n factorial over n to the power of n, converges to 0. Okay, the next video will finish off this particular section. We'll talk about some of the geometric style sequences. Thank you.